So with that, it is my distinct pleasure to introduce Dr. Julia Kelson, who's visiting us from the University of Michigan. Julia is a stable isotope geochemist at her core with interests in modern and ancient climates. And she got a PhD in 2019 at UW in the Earth and Space Science Department, where she was an NSF Graduate Research Fellow. She went from there a couple of years ago, I guess a year and a half ago or so, to the University of Michigan, where she's been working with a number of faculty who are familiar to many here in the department, including Naomi Levin and Ben Passy. She's working on a postdoc there, picking up some new isotopic methods I'll mention in a minute. I'm sure she'll talk about extensively. And she's supported by an NSF Earth Sciences postdoctoral fellowship through her work there. Julia is, I guess, notable in that she is kind of developing expertise to become an expert in the laboratory analysis of traditional light isotope systems, but with a non-traditional twist, two non-traditional twists. So she likes to take easy measurements we've been making for a long time and make them hard to do, but oh so much more informative. And so she's been measuring and working with both clumped isotopes in carbonates, looking at bonding between multiple rare isotopes within the carbonate molecule, as well as now with the work at Michigan, getting into oxygen-17, the less well-known cousin of oxygen-18, but again, very useful, tough measurement to make, but one that can really add a lot to what we can learn from geochemistry of carbonates. And so she's developed expertise in both of these systems, and I think important to point out that she's been involved in a variety of ways in work with both of these systems now. She's made fundamental contributions to our ability to make the measurements, and to make measurements in reproducible and comparable ways across laboratories, which has really been hard for both of these systems, I think, but Julia's really kind of pushed the field forward, as well as developing our ability to interpret these and use them as paleo proxies and learn about past climate and environment from them, using a combination of those measurements and modeling to interpret the data that we get from them. Her, I guess, main system, and I think the one she's going to talk about today is soil carbonate, which again is one that's familiar to many at Utah. And I would point out that she's, actively involved in a variety of efforts as well to kind of improve mentorship with the focus on diversity, equity, and inclusion at both of the institutions that she's been in. But even now, as just a second-year postdoc, she reports having mentored 7 different undergraduates at various times during her PhD and postdoc, as well as a high school student who produced a publication that's now in review. And so she's kind of been highly engaged in trying to help mentor the next generation of scientists. And with that, I'm going to turn it over to Julia. You want to put up the slides?
Yeah.
Take it away.
Okay, so I'm assuming that you can see what you're supposed to see, and thank you for that nice introduction, Gabe. Hello, everybody. I'm Julia Kelson. I use she, her pronouns, and as Gabe mentioned, I'm currently a postdoctoral fellow supported by NSF at the University of Michigan, and I want to thank everybody for inviting me to tell you about my research that seeks to unlock the paleoclimate archives of soil carbonates with clumped and triple oxygen isotopes. So I want to start by showing this canonical record, which is the oxygen isotope composition of benthic foraminifera through the Cenozoic. And I'm showing this record in part because this isotope record is what got me excited and interested in paleoclimate research. And this record forms the backbone of our understanding of paleoclimate through the past 60 million years. And so this period of time in Earth's history provides ample opportunity for us to learn about extreme end members in the Earth system and climate in those extreme systems. So I'm particularly interested in greenhouse climates, like those of the early Eocene climatic optimum and the mid-Miocene climatic optimum, because these warm house or greenhouse climates can illustrate end-member conditions like potential future warm climates. This period of time also hosts several interesting climate transitions and hyperthermals that we can study that can provide insights into carbon cycle perturbations and feedbacks, where the Paleocene-Eocene thermal maximum is probably the most famous of these hyperthermals as a period of extreme and rapid warming in Earth's history. But transitions in between icehouse and greenhouse states can also inform our understanding of the Earth's system and help illustrate potential future changes in climate. However, this record has one kind of outstanding limitation, and that's that it's a perspective of deep ocean temperature. So it's based in the ocean. But I'm particularly interested in understanding how these climate events have played out in terrestrial environments. And so the bird's eye view questions that guide my research are what can Earth's past reveal about the climate system? But it's particularly important to study and understand these questions on land, because after all, we live on land. So we want to know how climate change has affected entire terrestrial systems and how it will affect terrestrial systems in the future. And so drylands like those of Utah host about 40% of the world's population, and they're especially vulnerable to hydrologic and climate change in a warming world. And so the big questions that I seek to address are how has surface temperature changed through Earth history, and how has the water cycle and hydrological processes evolved through Earth history? So these are pretty deceptively simple questions, but they're critical to understanding future climate states. But in order to address these seemingly simple questions about paleoclimates and paleoenvironments, we need a couple of things. We need materials that record those periods of time, or sedimentary archives, and then we need ways to read those archives. So my favorite archive is soils. And I think that these are some of the best archives that we have of terrestrial paleoclimate, because soils they make up the thin skin on the surface of the Earth. So during their formation, they're recording information about the atmosphere, the biosphere, and the lithosphere. And it's important to note that they're forming over hundreds of thousands of years. So they're integrating information about their environmental conditions throughout that entire time period. And so this is a really useful tool to understand terrestrial environments. And in particular, my favorite tools are stable isotopes of pedogenic carbonate. So pedogenic carbonate is carbonate that's forming in situ in soils. And it often takes the form of these really uncharismatic nodules. They're just like little balls of carbonate in the soil. And the main stable isotope tools that we have at our disposal to understand terrestrial environments from pedogenic carbonate are light stable isotopes of oxygen and carbon. And so delta 18O, or what's traditionally referred to as oxygen isotopes, can tell us about meteoric waters from which the carbonate formed. Delta 13C can tell us about plant communities, soil respiration, and is sometimes used as a paleobarometer or to investigate carbon dioxide concentrations. And then my specialties are these two new kids on the block, Cap 47 are clumped isotopes, which can tell us about temperature at which the mineral grew, and Cap 17O, which is the newer kid on the block that I'm going to tell you about today, that we think tells us about evaporation at the time of formation. And so my research can be described or characterized as an infinite time loop, where the motivation for my research is largely in understanding future climates so that we can, or being able to predict future climates so we can plan and anticipate climate change. And the best way that I know how to do that as a geologist is by looking at past climates and learning what we can from the climate systems, both as analog climates and as learning how the Earth system works. But the nexus between predicting future climates and understanding past climates is the present. So we need to develop stable isotope tools and then understand how the proxy systems work through studies of modern environments. And then applying all of the above to the geologic record. So for the rest of this talk, I'm going to spend most of my time in the present. So I'm going to talk mostly about developing stable isotope tools and understanding what they mean in modern environments. Then I'm going to give you a brief example and kind of whet your appetite with some of the paleoclimate applications that I'm excited about. And then I'll save some time to discuss my vision for future efforts in scientific research and in making the geosciences a more diverse, equitable, and inclusive field. So today I'm going to tell you about the main challenges and developments in reading the archives of soil carbonates, and I'm going to discuss paleothermometry and clumped isotopes, and then I'm going to move on to paleohydrology and triple oxygen isotopes. And I'm going to talk about these efforts separately, but it's important to note that these are really complementary tools that we can use to read, that we can use to inform our understanding of paleoenvironments from soil carbonates. So carbonate clumped isotope thermometry. What is it? The carbonate clumped isotope thermometer is a study of the relative abundance of carbonate molecules that have both heavy oxygen and heavy carbon clumped together in the same molecule. So here I'm showing you the clumped molecule that has a heavy 18O and the heavy 13C clumped together in the same molecule. And what we analyze is CO2 that has a mass 47, and so that's the cap 47 notation. And these carbonate molecules can be measured in any kind of carbonate material. They're not limited to soil carbonates. It could be a shell or a limestone or a fault vein. And what's important, or what you need to know for the purposes of this talk, is that the abundance of these clumps relates to temperature. So we see fewer of these clumped molecules at higher temperatures. And this is because of a slight difference in the bond strength when you have both of the heavy isotopes in the same molecule. It's actually slightly more stable configuration, but the stochasticity at higher temperatures overcomes that bond favorability. So it's based in thermodynamics, and that means that it's independent of the fluid composition from which the mineral grew, which also means that we can use this clumped isotope temperature and the delta 18O measured of carbonate to actually reconstruct the delta 18O of parent water, independent of temperature. But because it's based in thermodynamics, you should be able to grab a carbonate of any kind, measure the clumps, and then predict the growth temperature. So this is an extremely powerful tool for understanding paleoclimate because it gets at what's one of the basic parameters of climate, which is surface temperature. Okay, but developing proxies is not always a smooth road. So I'm going to show you the hero's journey of a proxy, of all proxies, but in particular the clumped isotope proxy, where at first when the proxy is envisioned and the initial measurements are made, there's a lot of hype and a lot of excitement, but probably not a lot of confidence in the measurement. And then as you learn about the limitations of the measurement and perhaps discover some problems in standardizations and precisions, the proxy can go through the humble tumble and reach the pit of despair. And then through more research, you start to realize what the proxy is useful for, what its limitations are, and how to make good measurements of that isotope. You can reach the plateau of productivity. So when I started my PhD, clumped isotopes was more or less in the pit of despair. And through my dissertation and other international collaborators, we've reached the plateau of productivity. And so I'm not going to drag you through the details of calibrations and standardizations that allowed clumped isotopes to reach this maturity, but I want to impart upon you that I have led many of these research efforts that have allowed this method to reach its potential. So as an early graduate student, I independently designed experiments to rule out the main causes of calibration discrepancies and published what's the first unity calibration, the first step towards a single calibration for the clumped isotope community. And then in that work, I uncovered the importance of using the appropriate constants in calculating Cap 47 that had ramifications, implications for the entire clumped isotope community. And I've participated more recently in international collaborative efforts that have really led to broad agreement on standardization schemes and calibrations. And to show you what that looks like a little bit, this is what the calibration woes looked like in the early days of clumped isotope thermometry, where we weren't really sure what the temperature should be once for a given Cap 47 value. This is what you've read clumped isotope papers from the mid-2000s, you probably read about the too slow problem and said, yeah, gross, I want nothing to do with this proxy. But now I want to reassure you that if you had been hesitant to take that vaccine 10 years ago, I wouldn't have blamed you, but now the clumped isotope vaccine is both safe and effective. And so we're well past the too slow problem. So through thousands of replicates and thousands of analyses, the clumped isotope community has unified around a single calibration and a standardization measurement. So now we can confidently calculate temperature within 2 degrees Celsius or so, given the Cap 47 value of a geologic material like a pedogenic carbonate. So this is great. We're ready to understand big questions in the Earth system about temperature gradients and temperature change. This is an easy application to the geologic record. But of course there's a but, and the outstanding but is, do these isotope values have a seasonal bias specifically in pedogenic carbonates? And it's really important to understand the seasonal bias in pedogenic carbonates, in particular in clumped isotopes, because the seasonal range and surface temperatures at mid-latitudes can be something like 20 degrees Celsius. And this is a factor of 2, if not more, larger than the difference than the secular climate change that we usually wish to reconstruct using clumped isotopes. So for example, we think that on land, and the difference between the last glacial and interglacial was about a 5 to 10 degrees Celsius difference. And so you could imagine a scenario where you are trying to reconstruct a temperature change through time, but what you're really reconstructing is a change in the seasonal bias of your proxy, and which tells you something about climate, but it might not be what you think. So we really need to understand and characterize the seasonal bias of pedogenic carbonates in order to interpret those clumped isotope temperatures. And the outstanding assumption that most paleoclimatologists made, including myself and my collaborators, is that soil carbonates form in the summer. They form in something like mean growing conditions, and so the clumped isotope temperatures are generally summer temperatures. So I'm going to evaluate this assumption, the validity of this summertime bias, in a couple of different ways. First, I'm going to show you I've tried to evaluate this assumption using Holocene or near modern soil carbonates in places where we've collected soil carbonates, we've measured the clumped isotope temperature, and then we've stuck an honest to goodness thermometer in the soil. And so we know what the mean annual air temperature and the soil temperature was at those localities. So I compiled all of the existing clumped isotope data for near modern soil carbonates, brought them up to reprocess them and updated them according to 2020 community standards. We can use this data to evaluate whether or not soil carbonates are actually forming in the summer. And if in this figure of mean annual air temperature versus clumped isotope temperature, if a single soil carbonate falls on the 1-to-1 line, it suggests that that carbonate has no seasonal bias. If it falls above the 1-to-1 line, then it suggests that there's a warm season bias in that clumped isotope temperature. Okay, so generally, yes, soil carbonates are forming in the warm season based on their clumped isotope temperatures. But there's a lot of variability in the magnitude of this seasonal bias. So some of these soil carbonates are forming in temperatures that look like mean annual air temperature, and some of them are forming in temperatures that look like they're 20 degrees Celsius hotter than mean annual air temperature, which is actually even hotter than summer temperature and summer air temperature in most of these environments, suggesting that there's potentially radiative heating that's elevating soil temperatures above that of air temperatures. So we need, in order to really understand what's causing the magnitude of the difference in the seasonal bias, we need to understand the process, but that's how are soil carbonates forming, and then by extension, when are soil carbonates forming? So let's go back to our outstanding assumption that soil carbonates form in the summer, and think about the chemistry to partially explain why we originally assumed that soil carbonates were forming in the summer. So this equation encapsulates the chemistry behind calcite formation in soils. So calcite will form given supersaturation, which relates to the concentration of calcium ions, the concentration of carbon dioxide or PCO2, And then it also is temperature dependent based on these equilibrium constants, or the Ks. And so calcite will form if there's an increase in calcium concentrations, a decrease in carbon dioxide concentrations, or an increase in temperature. And all of those things are really likely to happen during soil drying, because drying will both increase ion concentration. It might promote degassing of CO2. It might turn off microbial respiration because it's dry and the microbes aren't happy. And it's also really likely to happen during warmer temperatures. So this will often yield a warm season bias, but it also yields another prediction that we can test, which is that it's not summertime that's important, or when the warm season occurs that's important, but instead it's that the timing of rainfall should be important in controlling when soil carbonates form. So we can go back to our compilation of near modern soil carbonates and see if some of this variability can be explained by the timing of rainfall alone. And this was based on a hypothesis from a single climate transect in the Andes, where the workers originally discovered that in this one place where it rained too much in the summer, where there was a large monsoon, the soil carbonates didn't form because the soils were too wet in the summer, versus if it rained in the winter, in the summertime, the soils were able to dry out. So the soil carbonates generally had a larger warm season bias. However, we don't really see this hypothesis holding true when looking on a global basis. And so there actually is a statistically significant difference in the magnitude of the seasonal bias between the summer wet soils and the winter wet soils, but there's certainly a lot of overlapping ranges. So this isn't a correlation that I would necessarily hang my paleoclimate hat on and use simply in the geologic record. So it looks like empirical data doesn't provide a controlled way to test this hypothesis. There's multiple factors that are contributing to seasonal bias in each of these soils. So another tool that we can use to explore the seasonal biases and start to understand process is numerical modeling. So I've used a model called HYDRIS. It's a 1D numerical model that couples the equations for calcite chemistry with water transport, heat transport, as well as CO2 production, the carbon dioxide production. It was developed in the 90s, mostly to be able to predict soil moisture for agricultural purposes. But I'm taking this developed model and using it, repurposing it for my purpose of understanding the seasonal bias of soil carbonates. And so I'm seeking to test how does the timing of rainfall change the timing of soil carbonate formation, and a really simple thought experiment by forcing the model with a climate record from the semi-arid Rocky Mountains, where there's a summer monsoon that rains in the late summer, and then shifting that rain by 6 months and changing nothing else in the model to understand how that affects the physical and chemical parameters at depth in the soil, and when it affects how calcium carbonate forms. So we do see a shift in both peaks in water content and CO2 content in these different simulations. And because water content and CO2 content are two of the dominant physiochemical parameters that control when calcite forms, we also see that shifting this rainfall changes in the model the timing of calcite precipitation and dissolution. So it's not particularly easy to visualize this from this figure alone. So I'm going to plot the volumetrically important calcite based on the time of year that it formed. And what we see is that in the winter wet simulations, calcite forms earlier in the year, and in the summer wet formations, there's kind of a double hump where it forms a little bit in the spring and a little bit in the fall. So this is a significant finding. It suggests that rainfall is really a top-down control on the timing of carbonate formation. I didn't show this result specifically, but we confirmed some of the work from Tyler Hughes and others that calcite forms in what looks like discrete drying events that follow rainfall. And part of what's causing that is the feedbacks with CO2 production. So plants and microbes are really important and play an important role in controlling when this inorganic calcite is forming in the soils. And so for paleoclimate, what do we do with this information? I think there's still work to be done to continue to understand how the system is working and what the seasonal bias is doing. But it also suggests that if we can integrate information external information about the timing of rainfall, sediment, like grain size from sedimentology, then we can amplify information that we have from isotope records. And I've thought mostly about the implication for clumped isotopes, but it's worth noting that this has implications, the seasonal bias has implications for all isotope measurements that are measured in pedogenic carbonate. I also want to point out that this type of work, it can be a really good way to involve undergrads. So I had an undergraduate who was really interested in getting her hands on samples and starting on paleoclimate research, but wasn't allowed in the lab because of COVID. And so she started working on modeling greenhouse climate states and seeing if this seasonal bias and this importance of rainfall also holds true under a different climate state. And so this work it's starting to build a bridge between proxy data and climate model data. So we're producing all these isotope records, but if we can't translate them into meaningful climate parameters, then it's not as useful for understanding the Earth system. So we need to understand exactly what these isotope values represent so that we can compare them to models. And this builds, again, on work from Tyler Hughes, Gabe Bowen, and his student Brendan, working on proxy system modeling so that we can start to do data assimilation exercises between proxy data and climate model data. Okay, so that was an overview of how I've used clumped isotope thermometry and pedogenic carbonates to advance paleothermometry. Now I'm going to move on to paleohydrology and triple oxygen isotopes. So so I'm going to tell you about this emerging tool that will enable reconstructions of the hydrologic cycle. And triple oxygen isotopes refers to paying attention to 17O, where usually delta 18O, we're just looking at the ratio between 16O and 18O. So now we're also thinking about delta 17O, the ratio between 17O and 16O. And to give you some context, if clumped isotopes have reached the plateau of productivity, triple oxygen isotope measurements are somewhere back towards somewhere between either initial hype or humble tumble, depending on who you ask. And so it's really the early days, which means that there's a lot of potential and a lot of places where this proxy could go. So I already told you about one isotope, big delta, that's hard to measure and has low precision. So why on earth should we bother with another big cap 17O measurement? And so to explain why I'm interested in triple oxygen isotopes, I think it's important to remind you all what we do with delta 18O, or what we would like to do with delta 18O and pedogenic carbonates. So delta 18O, or what's typically referred to as just oxygen isotopes, is really a superstar in modern hydrology and paleohydrology studies. And it's a useful tracer for hydrologic studies because oxygen isotopes are progressively distilled during rain out of atmospheric vapor. And so it can be a tracer for all of these useful things like equator to pole temperature gradients, the amount effect in monsoons, identifying where moisture sources came from, how much recycling there's been, and paleoaltimetry, or reconstructing ancient elevation gradients. However, all of these really useful applications of delta 18O have been limited in terrestrial paleohydrology because of the potential for evaporative overprinting. So evaporation will also will enrich oxygen isotopes. And so this is, basically the problem is that delta 18O is non-unique. It tells you all of these things, but we need another constraint, especially to understand evaporation in terrestrial systems. So evaporation really throws a damp towel, so to speak, on our ability to interpret delta 18O in the geologic record. And this is where triple oxygen isotopes comes to the rescue, where we can use it to fingerprint evaporation in the geologic record. And so the way this works is that delta 17O is about half that of delta 18O. And note that I'm using delta prime notation, which is a logarithmic notation of the familiar delta. And equilibrium processes like Rayleigh distillation will cause delta 18O and delta 17O to evolve along a line that has a slope of 0.528. And in contrast, kinetic processes like evaporation will cause evolution along a line of a slope of 0.5185. And I know that those numbers sound like they're nearly identical. They would both round to 0.52, but it's a small deviation that's both measurable and provides the basis for the entire field of study. And usually when we plot this data, we rotate this 90 degrees on the axis 90 degrees, so that primary waters that undergoes Rayleigh distillation, that's unevaporated, looks like a flat line, and then evaporated waters fall below the flat line, where an increasing evaporation causes a depletion in cap 17O and an increase in delta 18O. And so for those of you who work in modern hydrology, you're probably familiar with deuterium excess or D excess, which is an isotope of hydrogen that's exactly analogous to how 17O excess or cap 17O works. However, in the geologic record, hydrogen isn't preserved in the same mineral phase. And so what 17O brings is the opportunity to be able to apply this common framework of fingerprinting evaporation directly to the geologic record through measuring it in a carbonate mineral. And to further illustrate the power of 17O, I want to show you a couple of waters, and that delta 18O can sometimes be ambiguous. So the Great Salt Lake in your backyard has a delta 18O of about -6 per mil. The Huron River in my backyard in southern Michigan also has a delta 18O of about -6 per mil. However, these two bodies of water have undergone very different histories, where the original rain that fed into the Great Salt Lake was isotopically much later. It's been sitting as a bathtub and evaporating. The Huron River in Michigan is more of a flow-through system, and so it's essentially unevaporated water. And so you don't see that in the delta 18O, but you can fingerprint that in the cap 17O, where the Great Salt Lake has a much lower cap 17O value. So this method sounds great. Why isn't it wildly popular? It's not popular yet because it's a really technically challenging measurement. So typically stable isotopes of carbonate, of carbon, delta 18O, delta 13C, and clumped isotopes are measured as CO2. However, there's an isobaric interference between 17O and 13C. So we need to convert the carbonate into O2 to measure the cap 17O. So I'm working right now with the best in the business, Ben Passy and Naomi Levin, who have designed a reduction fluorination system to measure 17O in carbonates. And we're particularly proud of the cobot, the so-called friendly robot arm that moves the dewars around for us while we do other more productive things. That was implemented just about a month ago by graduate student Nick Ellis. So this is a breakthrough in our ability to automate 17O and soil carbonates. So what the work that I'm doing to advance 17O is understanding the variability in the patterns in Holocene or near modern soils on a global scale. And so we need to understand how 17O works and what it means in modern soils before we can apply it to the geologic record. And the basic prediction that I made is that 17O indicates evaporation. It's sensitive to evaporation. So on a global scale, this should relate to aridity. I'm defining aridity as the balance between mean annual precipitation and potential evapotranspiration. And so I've collected samples across the world, a little bit through strategic fieldwork, through places that I could drive to from AGU a couple of years ago, and then also a little bit of fieldwork in my backyard in southern Michigan. And I've sought to collect soil carbonates from the hyper-arid places like the Mojave Desert all the way up to the humid and subhumid environments that are the limit of places where soil carbonates form. And so the first step in understanding 17O and identifying is to compare the 17O of soil carbonates to that of meteoric water to see if do soil carbonates look evaporated. So these gray dots are the range of unevaporated meteoric waters. And then to remind you what the evaporation trajectory looks like, it's a depletion in 17O and enrichment in 18O. And to give you some context for what a lot of evaporation looks like in terrestrial systems, I'm showing the Great Salt Lake and the Pyramid Lake, which are both terminal lakes that are essentially bathtubs. And so this represents what an extremely evaporated terrestrial water looks like. So what do soil carbonates look like? It looks like soil waters range from unevaporated to very evaporated. And you would not be able to identify this evaporation with delta 18O, but we can identify it with cap 17O. And it also suggests that we were right to be worried and hesitant in interpreting delta 18O of soil carbonates previously, because in at least some settings, that value has indeed been overprinted by evaporation. But the plus side is that 17O can help us identify and account for that evaporative signal. And I also want to note that this, what I'm plotting are the water values calculated from soil carbonate. So it represents the soil water integrated throughout the entire hundreds to thousands of years of that soil carbonate formation. So it's not just an instantaneous or ephemeral evaporation that's represented as a single drying event. Instead, this is persistent evaporation and the persistent dryness that's causing depletion in 17O in these soil carbonates. So to continue to illustrate how 17O can be useful in identifying evaporation, I want to show you two depth profiles in a soil. So on the left is a soil from Tibet that has obviously experienced near surface evaporation, as indicated through the enrichment in delta 18O in the surface alone. And so you might look at the soil as a paleoclimatologist and assume that the delta 18O of water at depth you can reasonably expect that to represent unevaporated meteoric water. And then on the right is a soil from the Andean Piedmont near Mendoza, Argentina, that has uniform delta 18O with depth. And so without further information, you probably assume there hasn't been evaporative overprinting in the soil, that you could use this delta 18O to represent meteoric water. However, cap 17O reveals that there's actually been quite a bit of evaporation in both of these profiles. So in Tibet, we see a low 17O value near the surface and a high 17O value at depth. That confirms our suspicion that, okay, these near surface soil carbonates look evaporated, but the ones at depth probably look fine, and these are probably a good representation of meteoric water. But in the Andes, we see that there's been some sneaky evaporation. So we see uniformly low 17O values at depth. That suggests that these carbonate values at all depths have been formed in water that's been evaporated. And what's interesting about this is it also suggests something about the mode of soil carbonate formation. So in Tibet, it's probably drying from the surface down and then drying from the surface down that's promoting soil carbonate formation. In the Andes, however, there must be some kind of mixing, evaporation and then mixing of that water, and then evaporation and then mixing of that water to produce what looks like uniformly evaporated water at all depths in the soil column. And we can check for that evaporation because these are near modern soil carbonates. We know what the delta 18O values of meteoric water should look like. And indeed, for this Tibetan plateau, the soil carbonates formed at depth look more or less like what we would expect from meteoric water. And the delta 18O from the Andean Piedmont is calculated waters are 4 per mil heavier, at least 4 per mil heavier than meteoric water. So indeed, there has been a lot of evaporation. Okay, so another way to look at this data altogether is to see if it conforms with our prediction that we should see low 17O values in more arid environments. And it looks like there's a relationship with aridity, but like most things relating to soils, it's not really simple. Instead, what we see is more of a wedge in relating to aridity. So this conforms with our expectation that in humid and subhumid environments, there's not a lot of kinetic evaporation, and that 17O is staying relatively high. But as you move to semi-arid and hyper-arid environments, you see a pretty large range in cap 17O in the soils. And so this isn't going to be a simple like plug and chug or measure cap 17O and get aridity out of the soil. But I wasn't actually expecting that, and I don't, it might be that in a single environment where you have calibrated to be that, you have calibrated it. But instead, I think that this is actually more interesting because it suggests that there's differing modes of carbonate formation in these different environments, or even within these categories of aridities, within these single places, the soil carbonate is forming in different ways. And there's a variation in the hydrological processes, probably on a single ecosystem bias, or even within a single soil profile that's causing a variation in CAP 17O. And so I think that there's a relationship between transpiration and increasing proportion of evaporation. So in these more mesic environments, soil dewatering is probably happening largely as a result of plants transpiring and moving the water up through the soil, which doesn't fractionate isotopes. Versus in these semi-arid to hyper-arid environments, there's probably an increasing proportion of evaporation that will fractionate. But again, it's this variability that's really interesting. And so those are the next steps for this work, is to really dig into that wedge and explore what controls the variability of 17O in semi-arid to hyper-arid environments. And so it all gets back to understanding soil processes. I want to understand how much water storage there is in a single ecosystem, and when and where soil water is removed through evaporation versus transpiration, and how that varies seasonally. And so the next way to do that is by measuring all of the ins and the outs in the soil profile. So the CAP 17O of rainfall, the CAP 17O of soil water, and then also measuring the balance of transpiration and evapotranspiration during the window of carbonate formation. So I think that this would be a great use of the soil water isotope storage system and the ISO wagon that was developed in part at the University of Utah. So in summary, it looks like 17O is going to be a really useful tool to identify and account for evaporation in soil carbonates. And this will allow us to use delta 18O in terrestrial environments for all of those original things that we wanted to use delta 18O for. So like understanding moisture sources and understanding gradients in temperature. And so it opens up terrestrial paleoclimate. It opens up the use of delta 18O to arid environments where we previously have been really struggled to find good records that tell us about the water cycle, largely because we thought that the delta 18O was overprinted by evaporation. So these were really complementary tools, both clumped isotope thermometry and triple oxygen isotopes, that can help us read the paleoclimate archives of soil carbonates. So I just spent a lot of time in the present, and I want to whet your appetite a little bit and give you a sense for the types of questions that I'm interested in going after with these tools. So my past paleoclimate work has really sought to understand greenhouse climates like those of the early Eocene. We've known qualitatively for a long time that the Eocene was a warm period. This is largely based on the discovery of crocodilians and palm fossils at polar environments. And so this tells you that the Earth climate was at a very different state. And it also raises the question that if you had near tropical temperatures at the poles, then what was it like at the tropics? Was it, were the temperatures just scorching so that nothing could live? So what were latitudinal temperature gradients like in these greenhouse periods? And is it the same in modern climates? And how can we expect that to change in modern climates with warming? And then a related question was the magnitude of seasonal variation in temperature the same as in the modern? And then what was the hydrologic cycle like during this time period? Was it wetter? Was it drier? And I'm working on a record right now from the Golar Formation where I think I found evidence using triple oxygen isotopes that there were some really light isotopes and potentially snow in what should have been a really hot house climate. So I've sought to address these questions mostly in the Western US using my favorite tools of stable isotopes and pedogenic carbonates and oyster shells. I also want to say that excellence in diversity, equity, and inclusion is really integral to accomplishing all of this science. So I've been involved in outreach efforts to serve underserved communities and highlight the potential for STEM careers. And we're fortunate in the geosciences that our labs, like isotope labs, as well as outdoor settings, are really great opportunities for outreach and good ways to hook people in the field. And I'm really passionate about mentoring both graduate or in the future graduate students, but graduate and undergraduate students, and also mentoring across peer groups. I've been involved in the American Association for Women in Science, where we mentor across different levels in the university. So as an assistant professor, I would really look forward to the opportunity to be able to directly recruit diverse graduate and undergraduate students and plug into some of the community efforts that I heard you guys talk about today during meetings to promote diversity in the field. And then switching back to research, I want to tell you about outlook and future directions for both clumped isotopes and 17O. So I think that clumped isotope thermometry has, it's really reached the plateau of productivity. And so it's poised to tackle some of the big questions about Earth's surface temperatures. I'm particularly interested in warm periods like the Eocene and the Pliocene, because I think that we can start to nail down questions about Earth system sensitivity, which is the temperature response to a certain greenhouse gas forcing for critical periods of Earth's history. And I'm also interested in seasonality. So smaller and smaller sample sizes and clumped isotopes can start to let us get at seasonally resolved climate records in deep time. So we can do this through shells. This is a picture of a shell that an undergraduate has carefully drilled individual spots so that we can start to get at seasonal resolution. There's also plenty of opportunities to collaborate, and especially in understanding faults and fluid histories and diagenetic histories. But I'm particularly passionate about paleoclimate. So 17O, again, we're a little bit further back on the curve here, where I think that 17O has a lot of promise. It's still very much the early days. And so a lot of my work in the next 5 years will be developing 17O in modern systems and then some early applications. So I already kind of described this, but I think the first thing is that we need a more systematic study of 17O in soils through measuring soil waters and rainfall, and particularly critical zone observatories are going to be a great place to do this, where we have measured a lot of different things in soils and can start to plug in our understanding of soil and hydrological processes with 17O. And the best targets for climate records are places to apply 17O, are places where we expect large changes in delta 18O or large changes in aridity. I also think that it's going to open up paleohydrology and paleoaltimetry in places that have been challenged by moisture recycling. So places like the Tibetan Plateau and the Indian Plateau, where there's extreme rain shadow. And so we can start to understand the elevation history of those places using CAP 17O. And then looking forward more to something like the next 10 to 20 years, the applications of 17O really span the Earth system, and they're not limited to soil carbonates. So part of what I love about working with stable isotopes is that these tools can cut across disciplinary boundaries. And this is especially true for CAP 17O, because any application that you might want, that you use delta 18O for, you might be interested in CAP 17O because it can give you another constraint or another way to understand why delta 18O varies. And it's possible to make this measurement, and will be possible to make this measurement in biological materials through combustion, and it's currently being made in cherts. And so this opens it up to applications like the atmospheres, where there's actually a gigantic signal in O2 and 17O, and relates to the concentrations of CO2. So it's potentially a paleobarometer for carbon dioxide. It, I think, will be increasingly useful in the water cycle, and because it doesn't have the temperature dependence of deuterium excess, it should be useful in marine settings. It could be useful to understand faults and fluid migration and lake systems, as well as weathering in the critical zone and carbon cycling in the critical zone. So, what I love about stable isotopes is that you can apply them to understand all these different types of questions. And so I want to end with this because I work so hard at developing stable isotope tools, in part because they can give us new perspectives on old questions, but also because they can reveal new interesting questions about the Earth system. So sometimes these new, we can run around with our hammers, and developing new hammers, but also sometimes it's worth it because they can lead to new nails. So with that, I'd like to thank my funding sources. Most of what I showed you today was funded by NSF. And thank you for your attention, and I'll take any questions.